Okay, we're gonna go over entanglement, this module, and contrast it, or not contrast it to superposition, but understand that superposition and entanglement are two of the most important properties for quantum computing, and to create the circuits later that we see. Okay, so the first circuit we're gonna look at is the Bell pair circuit. So what this does is it takes two qubits, Q0, Q1, and after applying this circuit, it will transform it so that they are perfectly correlated with each other, or in other words, they are entangled. So let us trace that circuit. So it's Q0, Q1. We have a Hadamard gate right here. Yeah, that's good enough. Hadamard gate right there, and then we have a C0 right here. Okay, so what this circuit does is it takes whatever state Q0 is in, and it applies Hadamard to it to put it in a superposition, and then there is a CNA operation applied with Q0 being the control qubit and Q1 being the target qubit, and this will produce the Bell pair state. So let's trace it as an example. So first, the qubits start in the state 0, 0, and next the Hadamard gate is applied to Q0, and the identity is applied to Q1. You can think of it as it doesn't need to be there. You don't need to apply anything, but if you wanted to, you could do that. So the way to write this would be H tensor product I, and H tensor product I with two matrices I will write on the side in a second, but in general, A tensor product B for matrices is going to be, I believe, each element of A, so A11 times B, A row 1, column 2 times B, A21 times B, and then A22 times B. And if you further expand that, you'll get something like A11, B11, A11, B12, A11, B21, A11, B22, and you will have similarly 4 entries right here, 4 entries right here, and 4 entries right here, so you get a 4x4 matrix. So that's how you take tensor products of two matrices. And what that does is when you say H tensor I, that means apply H to this left qubit right here, and it means apply I to the right qubit right here. So let me say that one more time. If there is a series of gates applied, like U3 tensor, U2 tensor, U1, onto some 3-qubit system, Q0, Q1, Q2, or I can write it in a big endian order as well. What happens is the leftmost product in the tensor product applies the leftmost bit, or leftmost qubit. The middle one will apply to this one, and the rightmost will apply to the rightmost one. And that is what's going on here. So in this example, H is being applied to this left qubit, and I is being applied to this right qubit. And if you wrote it in matrix form, you would get a similar result given the basis state representation with vectors we now know, where, like, for example, 0, 0 corresponds to this vector. So the same way you'll get a result that agrees with your intuition once you actually multiply this out, and you can follow the steps we do next, and you'll get the exact same result using the matrix form as well. I'm going to skip that just though for time. So if you apply this tensor product to this 2-qubit system, then you get H applied to 0, which takes you to positive, and I applied to 0 keeps it as 0. So now this is your vector. And this is also equal to, remember, if we expand the plus, that's equal to 1 over square root of 2 times ket 0 plus ket 1 times ket 0. And here you can now, since 0 for the second qubit is kind of deterministic, I could say, it can be appended to both of these two kets right here. So you have 1 over square root of 2, 0, 0, and this 0 comes from that right there, plus 1, 0. Again, this 0 will come from there, and that is the equivalent state after applying Hadamard to the first qubit, Q0. And sorry, this is written in, I might have said Q1, Q0 earlier, but this is Q0, Q1, because Hadamard is applied to the first qubit, which is Q0 right here. So you have to be consistent with that. Next, the state at this step after applying the C naught. So what happens when you apply a C naught to this? I should put a parenthesis right here. When you apply C naught to 0, 0, nothing will happen. And when you apply C naught on the first qubit, Q0, this 1 as a control will flip Q1 to a 1 as well, so you get 1, 1. And this is the Bell pair state. So what this circuit design does is it takes 2 qubits initialized at 0, 0, and it puts them in perfect superposition between the basis state vectors 0, 0, and 1, 1, and they are perfectly entangled. They're also called correlated states, and there are several other Bell states. So this is the Bell state beta 0, 0. There's also Bell states beta 0, 1, which would look like 1 over square root of 2 times 0, 1 plus 1, 0. These are called perfectly anti-correlated states, not uncorrelated, anti-correlated, which means they have completely opposite outcomes. So what this means with correlation and entanglement here is that if you're looking at this system right here and you measure the first qubit, that instantly tells you about the second qubit, what it is deterministically, right? Because if you get a result of 0, 0 with 50% chance, you're going to measure the first qubit as 0, which means you instantly know the second qubit has to be a 0 as well. There's no outcome in which the first qubit is 0 and the second qubit is 1. In the same way, if you get a 1 for any of these 2 qubits, you know the other one is a 1 as well. So that is what it means for 2 qubits to be entangled or correlated. Finding information about 1 qubit will give you perfect information about the other one. And the same way here, you know that it's perfectly anti-correlated. So if you measure 1 to be a 0, then you know the other one is a 1. Vice versa as well. There's 2 more Bell states, which aren't important to memorize, but just know they have phase flips, so like sign differences. So like instead of a plus right here, you can have a minus, and instead of a plus right here, you can have a minus. So those are the 4 Bell states. Okay, I will quickly mention that, remember the gates that you apply in quantum computing, that they can always be reversed just by applying an opposite, or by applying the Hermitian conjugate of the matrix as formed when applying these 2 gates in sequence. For Bell pairs and for disentangling 2 Bell pair states, it just happens to be the exact same operations in reverse order. So if you applied this in this dotted box, that's going to disentangle the 2 states and return them back to the original state they started in. Okay. And now let's look at a test for entanglement. So if you have 2 qubits and you're wondering if they're entangled, you can look at this test to consult if they are or not. One more thing before we do that, the tensor product for matrices is right there. For vectors, V1 tensor V2. The way to compute it is if V1 is composed of A, B, and V2 is composed of C, D, you do A times C, and you put that result in this top entry. You do A times D, you put this result in this entry, you put B times C, entries right here, and then B times D is down here. So what does this kind of show you? It shows you that there's like a logical connection between a 2 qubit system with a 1 qubit system with 2 to the 1 entries, and a 2 qubit system with 2 to the 2 entries for vector representations of the possible states that the qubits can be in, or the qubit system can be in. So for V1, V2, let's say they were ket 0 and ket 1. So 0 tensor 1 is equivalent to the state 0, 1. where q0 is 0 and q1 is 1. And if you wrote it in the form right here, then what is the probability amplitude for the ket0 vector? It's 1, 0, tensor 0, 1, and that's equal to it's equal to a 0, it's equal to a 1, and then it's equal to 0 and 0. And what is this vector exactly? Remember, I think I discussed this in a previous video. I'm not 100% sure, but each of these entries corresponds to, or the basis vectors for the 4 states. So the 4 possible states for the qubits are this, this, and this, and the basis vectors for each of these are 1, 0, 0, 0, 1, 0, 0, and so on. And this will be 0, 0, 0, 1. So this 0, 1, 0, 0 vector corresponds to 0, 1, using the same tensor product math, which is exactly the result we got right here. And one more thing to confirm, or like if you forget whether 0, 1 corresponds to this vector or 1, 0 corresponds to this, it's always going to be big endian order. So in big endian order, the rightmost is the least significant bit. This one's the least significant bit. So that's 2 to the 0 times 1 plus 2 to the 1 times 2. So this is just a 1. And then you would put that 1 right here. So it goes 0, 1, 2, 3, and so on for the indices. So you just match it in that index, and that's how you know that this is supposed to be the 0, 1, 0, 0 vector. Okay, so that's how to look at tensor product with vectors, and we're going to need that very shortly for the next step. Actually, should I leave that up? Maybe I should leave this up. We're going to look at that for the next step for proving the entanglement for Bell pair states. Okay, I'll make this smaller too. Whoops. Okay, great. All right, so now the test here is that if the joint qubit state space is not decomposable into component qubit state spaces, the qubits are said to be entangled. What that means is for a given state space, you should be able to separate or like factor it out, and then you can show it is separable. So let's look at an example where it is separable first. The equal superposition state, 1/2, where it's 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. This state space can be written as, if you factor the left qubit out from these two ket vectors right here, you get 1/2 on the outside, and you get ket 0 times, and it would be ket 0 plus ket 1. And you have, and actually you have to distribute this 1/2 to both of these qubits equally to normalize the probability amplitude. And I'm just going to put a 1 over square root of 2 right here. And then you will do the same on the other side where you pull out a 1 on the left qubit, and that'll be 1 over square root of 2 times, should I get rid of this parenthesis right here? I think this is confusing. Okay. It will be ket 1, and then that times ket 0 plus ket 1, and 1 over square root 2 times that. If you factor it again, this is the exact same thing as this. So we can bring this left side onto one factor, and we have 1 over square root of 2 ket 0 plus 1 over square root of 2 ket 1 times the exact same thing. If we pull out the 1 over square root of 2's as such, we get ket 0 plus ket 1, and 1 over square root of 2 times ket 0 plus ket 1. And this is exactly equal to the plus state and the plus state. So you can decompose this equal superposition into the 2 plus states for both qubits. So that's what it means for the 2, and this is also equal to plus tensor plus. So this is what it means for, or that's a plus and that's not a tensor symbol. The tensor symbol would be the x. Don't confuse that with this symbol, which means XOR. Okay, so this is the tensor between the 2 plus states. So this, since we were able to decompose this Dirac notation equal superposition into 2 vectors that are separable into separate qubit spaces, we say that they are not entangled. For a different example, let's look at if we're looking at the Bell pair, for example, where we know they're entangled, so we should get a different result. We have 1 over square root of 2 times ket 0, 0 plus ket 1, 1. And this cannot be pulled apart into any other tensor product of 2 qubits because both of the entries are unique from the other ket vector, right? So it's not like we can pull a 0 out because there's only a 1 in the other one. We can't pull a 1 because there's only zeros in the other one. Using this, there's also a way to write it in like a ket vector form. So what do we know about this ket 0, 0 vector? That's equal to, that's the tensor product of 1, 0 and 1, 0. Because remember, 1, 0 is the basis state vector for the qubit 0. Qubit 0, ket 0. So here we will get 1, 0, 0, 0. And if we did the same thing for 1, 1, we get 0, 1 tensor 0, 1. And we get 0, 0, 0, 1. And if we add the 2 together, because you can just use vector algebra here, we have 1 over square root of 2 times 1, 0, 0, 1. Okay, so now we need to be able to decompose it into 2 separate qubits to equal this vector. And let's assume that it is possible to do that first. So we'll use contradiction here. Let's assume it is possible to decompose into 2 separate qubits. Then if those qubits are Q0 and Q1, and Q0 is equal to some alpha 0, beta 0, and Q1 is equal to some alpha 1, beta 1, because these are the probability amplitudes of this qubit right here, where it would be like alpha 0 times ket 0 plus beta 0 times ket 0 for qubit 0. If we do the tensor product of these two, we get alpha 0, alpha 1, alpha 0, beta 1, beta 0, alpha 1, and beta 0, beta 1. And this vector is going to be equal to 1 over square root of 2 times this vector. An immediate contradiction should jump out. So we have that A1 times, so first of all, beta 0 times beta 1 equals 1. So neither beta 0 nor B1 can be 0, right? Otherwise that product would equate to 0. So then we know B0 is not 0, so A1 must be 0 for this to be 0. But also, if A1 is 0, then A0 times A1 can't be equal to 1. So just like that, we know there is no way, no configuration of probability amplitudes in these 2 qubits to be decomposed as a tensor product of 2 qubits. So there's no Q0, Q1 such that you can create this state right here. So that's how we know they are entangled. And it is the Bell state, and we know they're entangled anyways, so we can also use that as a little cheat if we needed to. So hopefully that should explain the entanglement test. There are several ways to do it. You can just try factoring it out instantly using the first example where they weren't entangled, or you can try using some kind of matrix logic to do that, or using the tensor product logic to do that. We can also do really quick as an exercise for where it was 1/2, 0, 0, 0, 1, 1, 0, and 1, 1. If we wanted to do the tensor product application here, then we know these are the vectors. I mean, it's the vectors 1, 0, 0, 0, 1, 0, 0, and so on. And if we add them, we'll get 1, 1, 1, 1, and 1/2 times all of this. And this is equal to what the result we got earlier. So for for Q0 and Q1, we had alpha 0, beta 0, tensor, alpha 1, beta 1. So we have alpha 0, alpha 1, alpha 0, beta 1, beta 0, alpha 0, beta 0. Yeah. No. Beta 0, alpha 1. Beta 0, alpha 1. And beta 0, beta 1. This actually does have a possible solution where every single entry is 1 over square root of 2. So 1 over square root of 2 equals alpha 0 equals alpha 1 equals beta 0 equals beta 1. And if you did that, you would get 1 over square root of 2 times 1 over square root of 2 is 1/2, which is each of these vectors entries given this coefficient right here. And so now if you take that back into this tensor product notation, we have 1 over square root of 2, 1 over square root of 2, tensor, the exact same vector. And what is this vector if you break it down into the Dirac notation? It's 1 over square root of 2 times ket 0 plus 1 over square root of 2 times ket 1, which is exactly the plus state vector. And ket plus was the exact result we got earlier when we did our manual factoring. So you can use either this tensor product notation and look for solutions, or you can just directly factor, and if you find a factor, you know they're not entangled. So that should explain all of the entanglement with tests, doing the test for it. And I will delete that now because I don't think we need that anymore. Okay, so now let's move on. And quickly, let's just, I'm just going to quickly highlight it because it's the prerequisite to the other circuits, the teleportation and superdense coding. A classically controlled gate can exist for quantum gates where you just apply the quantum gate depending on a classical bit value. So if it's a 1, you do it. If it's 0, you don't. Rather than having a dedicated qubit for that. Because we're going to have to deal with classical information bits in this algorithm. And we have to have classically controlled gates for that. So it's just simpler than a regular controlled quantum gate. But it's the exact same thing pretty much. Okay, so now let's go over quantum teleportation. So I'm going to actually open up the diagram I already created. So this is the quantum teleportation diagram. But before I explain what everything is, let's just talk about quantum teleportation. So the idea is there is some Alice who wants to send information about an unknown quantum state to Bob. So Alice has a qubit, Q0, and Alice wants to send the information and transfer it into Bob's Q1. And Alice has to do this without measuring Q0, because if Alice measures Q0, she'll measure it later in the actual circuit, but she can't measure it directly right now. Like forget the circuit on the left for now. That's not important. For Alice to be able to send this, Alice needs to devise some kind of schema, because Alice cannot directly read the information from Q0 and transfer into Q1. If she measures it, the qubit information collapses, and she cannot clone it because of the no cloning theorem. So if she wants to send Q0's information to Q1, she has to figure out a way to do that, and Q0's qubit has to be destroyed before Q1 gets the information as well. So it's quite a tricky challenge. But using quantum teleportation circuits, you can do that if you introduce one extra qubit, and Alice and Bob linked up, or I guess they met up somewhere and shared a Bell pair, which is also called an EPR pair, prior to this teleportation arrangement. So let us look at the actual circuit. So I think I labeled it here. So Alice has 2 qubits to her name. She has, and I'm going to use Alice's colors over Bob's colors, green and blue. So Alice has 2 qubits, and there are 3 qubits total in this circuit. Alice owns Q0 and Q1 and has it in her physical possession. And prior to Alice and Bob splitting up, let's say Alice is in North America and Bob is in Europe. Prior to Bob flying out to Europe, Bob was in North America with Alice and created a Bell pair between Q1 and Q2. And that bell pair is entangling the two qubits. So now any operations we're doing on Q1 will be transferred to Q2 because of their relationship. And it's you'll see kind of the indirect effect that it has later as we trace through the circuit. So we know that Q1 and Q2 are entangled, and Q0 is an additional qubit that Alice needs to introduce to be able to copy the information from into Q2. So Alice wants to replicate the information contained in Q0, and she wants to send that into Q2. She wants to teleport into Q2, destroying Q0 in the process before Q2 retains the information, or recovers it, is the better word. So let us quickly break down Q0. Remember, that's just alpha times ket 0. Also not alpha 0. Yeah, alpha 0 times, let's do alpha and beta instead of alpha 0 and alpha 1. We'll do alpha times ket 0 plus beta times ket 1. Okay. So that is what Q0 is. Just remember that for later. So the algorithm, we're going to trace what the state is of all these qubits as we go through. So let us first look at the starting state. So the starting state will look like this. So we already assigned Q0 to alpha times ket 0 plus beta times ket 1. So the starting state is Q0 tensor product with Q1, Q2. And Q1 and Q2 are the bell pair state. We already know that prior to them splitting up, or before Bob flies out to Europe. So we will write that as 1 over square root of 2 times ket 0 plus 1 over square root of 2 times ket 1. Okay, sorry, I made a mistake. I think I wrote just 0 here and just 1 here while doing the entire algebra explanation or expansion, and that might have confused you, so I'm just going to reset and do this example again. So Q0 is equal to alpha times ket 0 plus beta times ket 1 from above, from right here. And we're going to tensor product that with 1 over square root of 2 times ket 0, 0 plus 1 over square root of 2 times ket 1, 1. And the way to do this tensor product between two multiple term parentheses is to FOIL it out, like from algebra 2, where you do like this term times this term plus this term times this term plus this term times this term, and so on. So we'll have 1 over square root of 2 times alpha times 0 tensored with 0, 0. And this will just become 0, 0, 0. We know that from earlier. So I'm just going to remove that step and compute it immediately while writing this out. And this is going to become 1 over square root of 2 times alpha times 0, 0, 1, 1 plus 1 over square root of 2 times beta times 1, times the vector 1, 0, 0 plus 1 over square root of 2 times beta times the ket vector 1, 1, 1. Okay, so this is the entire state of the circuit prior to applying any actual gates or C naughts or anything. So I'm going to concisely keep this so that we can reference it later. Okay, and now after the first C naught, what happens is, after the C naught at this stage of the circuit, what happens is we take this expanded notation and we just apply C naught where Q0 is the control and Q1 is the target. So wherever Q0 is a 1, we flip Q1. So there's nothing here, nothing here, here there's a 1, and here there's a 1. So it will become, and I'm going to factor out the 1 over square root of 2 right now. So we have alpha times ket 0, 0, 0 plus alpha times ket 0, 1, 1 plus beta, and now we're going to flip because of the 1 in Q0, we're going to flip the next one, 1, 1, 0 plus beta, and we're going to flip the second one, so it's a 1, 0, 1. So this is now the state of the 3 qubits after applying that first C naught. Okay, now we are going to get rid of this former stage because we want to clear up space for ourselves because there's not enough space. So let us do that. And I'm going to erase this. Okay. Okay, now we want to measure at the next stage after applying Hadamard what happens. So let's use yellow again and draw what is going on in this state at this point in time. Okay, so at this point in time, after H, remember H is being applied to Q0, so we can do H tensor times Q0. So because we're not applying anything to the other qubits, this is the equivalent of H tensor I, where the identity is applied to the second and third qubits, and the first qubit, the Hadamard, is applied. So that should match this circuit column right here. And we'll apply that to this state right here. Rather than actually writing out the algebra, I will just expand it and tell you what it's supposed to be. So like if you went about this matrix way, what you would do was you would do I tensor I, which I believe is, it should be, remember from A tensor B, it was 1, so like the one entry from this I times I, 0 times I, 0 times I, and then 1 times I. And then off of this result, you would apply each entry of H to each of that vector again and again. So it would become a 8x8 matrix. But since that's pretty complicated, we can instead just do, we can look at the first qubit and put it into equal superposition between 0 and 1, depending on its value, right? So for example, on the very first entry, and I'm going to start writing it from here because it's very long, we have 1 over square root of 2 times, and let's look at the very first one. So alpha times this ket vector is 0, 0, 0. 0, 0, 0 with Hadamard applied to Q0 is alpha times 1 over, and I'll take the 1 over square root of 2 on the outside. 1 over square root of 2 times ket 0, 0, 0 plus ket 1, 0, 0. Because H applied to 0 puts it in equal superposition between 0 and 1. Remember the plus state. So this whole part comes just from that term right there. And applying it to the other steps as well, let us write out the rest of it. So this is plus alpha times 1 over square root of 2 times ket 0, 1, 1 plus ket 1, 1, 1. And now we're going to add the beta. Beta times 1 over square root of 2 times ket 1, 1, 0. And this time it is not plus, it's minus, because H applied to a 1 puts it into the minus state, where it's, remember, ket 0 minus ket 1. So we're going to get 1, 0, 0 minus 0, 1, 0. And we're going to add beta times 1 over square root of 2 times, instead of 1, 0, 1, it's going to be 1, 0, 1 plus, or not plus, sorry, minus, because of the 1 here instead is a minus, minus 0, 0, 1. Okay, so that is the full expanded notation of the 3 qubit system state after applying the H gate. And we will actually factor this out further so you can see one more important fact. So let us first recognize that we can pull out. How should we pull this out? Let's do this. We're gonna pull out the first two qubits. So because we're going to be measuring Q0 and Q1, we want to pull those out so that once we get measurement results, we instantly know information about the third qubit because it is entangled with the first two qubits. So let us pull out let's pull out 0, 0 as the first term. And let's first write 1/2 on the outside of all of this. And then we can get rid of all the 1/square root of 2's. Okay, so we have 1/2 and we're going to pull out the 0, 0. So in which portions are there 0, 0 in the front? Right here. So we have 0, 0, and I'm checking a slide to confirm this is... Okay, one small mistake I made. I looked back at the notes because it wasn't lining up. Here on these two steps, when I apply minus, it should be applied to this term, not the other term, because the minus state is equal to ket 0 minus ket 1, not ket 1 minus ket 0. So it should have been inverted, so that it should be minus ket 110 plus ket 010. So using this now, we can pull out the first two qubits. So we have 0, 0 coming from this term and this term. And this is times alpha plus beta. So it's going to be alpha times ket 0 plus beta times ket 1. And the 0 and the 1 are coming from the last qubit in each of these ket vectors. Okay. And this we're going to add to the next one we're going to pull out is a 0, 1. So which ones have 0, 1 in the front? This one has a 0, 1 in the front, and this one has a 0, 1 in the front. So we're going to pull out this, so it's alpha times 1, and because now this 1 is the last qubit there, and a 0 is the last qubit here, it's going to be beta times ket 0. And let us add 1, 0 times... now we have to be careful because there's negative signs. So 1, 0 we pull out from here. So we have alpha times ket 0, and we can get rid of that one. And I don't think I crossed out the other two when I pulled them out. So the 0, 1 I can cross out, and the 0, 1 I can cross out. And 1, 0 also gets pulled out from here, but it's a minus, so it's minus beta times, and the last qubit is 1. So we pull out a 1 there, and we can get rid of these two. Wherever it starts with 1, 0, we're going to delete that. I think we did. So the last two are these two. And we're going to add 1, 1 times alpha, and 1, 1 alpha is a 1 minus the beta is a 0. Okay, I think that should fully cover the breakdown. So now using this breakdown, we can note a couple things. So first of all, and perhaps most importantly, is the fact that we can decompose it so that we have 2 qubits first before all of these terms, and these 2 qubits are all the basis state vectors. So we know we've covered all possible options if we measure the first 2 qubits on what the third qubit is, right? And they're all unique from each other. So what I mean is that if we measured the first 2 qubits and we get 0, 0 as our result, then we know the third qubit has this qubit state right here. If we measure a 1, 0, a 1 on the qubit 0 and a 0 on qubit 1, then we know the third vector has this state right here, or the third qubit has this state right here. So because they are perfectly correlated, we have information about, they're not perfectly correlated, sorry, they are entangled. We have information about the third qubit just from the first 2 qubits, which is why at this stage, we're now going to measure the first 2 qubits, and that will give us information on how to reconstruct the third qubit. So remember, the third qubit let's say we measure the first two qubits, okay? Q0, Q1, let's say the first two qubits are 0 and 0. So we know the third qubit is alpha 0, alpha times ket 0 plus beta times ket 1. So how can we recover that into the original Q0 state from the circuit? Well, Q0 is exactly alpha times ket 0 plus beta times ket 1. So we don't need to do anything. And we instantly have Q2 is now the original Q0. And we've already successfully teleported the value of Q0 into Q2. Now let's look at Q0, Q1 is equal to 0, 1. If Q0, Q1 is equal to 0, 1, then we know the third qubit is alpha times ket 1 plus beta times ket 0. Well, now this is different from Q0, and we want alpha times ket 1 plus beta times ket 0 to be equal to alpha times ket 0 plus beta times ket 1, because that is the original state. So we know whatever the value, this is currently what Q2 is, we want to make this Q0, so we're going to apply a bit flip gate where we flip the 1 to a 0 and we flip the 0 to a 1. So that gate is the X gate. So once we apply the X gate to both the qubits, we will get the Q0 value. And the X gate applied to, let's do this actually as the example. So alpha times ket 1 right here is equal to alpha down here and a beta up here. And if we apply the X gate, which is 0, 1, 1, 0, that's going to be equal to alpha and beta. So that's how we know that's correct. So just like that, you can apply gates in sequence for the other qubits as well. So if we have Q0, Q1 is equal to 1, 0, this now has a sign, and we want to make it alpha times ket 0 plus beta times ket 1, but this is alpha times ket 0 minus beta times ket 1. So we apply a phase flip gate, which flips the phase for the 1 to become a positive, and it doesn't affect 0. 0 doesn't have a global phase. So for that, we're going to apply the Z operation. The Z gate, I believe, is 1, 0, 0 minus 1. So if we apply that to alpha and minus beta, we get alpha and beta. And then finally, if we measure these first two qubits and we get 1, 1, then to convert alpha times ket 1 minus beta times ket 0 into this, we need to apply both a phase flip gate and a bit flip gate. So we swap this to between a 0 and a 1, and then we apply a phase flip gate to beta to make this a positive. And we will recover our original qubit state up to a negative global phase. So we actually get this qubit vector once we do the operations, but as far as measuring, negatives don't affect measurement. So we're still going to measure and get 1, 1. So the state of Q0, the original state of Q0 can be, oh, sorry, I'm actually, I think I'm confusing something with, yeah, I'm mixing it up. I'm confusing with superdense coding later. You actually just do get 1, 1 directly once you apply phase flip and bit flip gate to this right here. So we can fully recover Q0 into Q2 by applying this circuit diagram here and using the fix-up code. So that fix-up code is captured right here. What this says is if B2 is equal to a 1, then we flip it. So yeah, these B2 and B1 are the measured results. So if B1 is the measured result of Q0, if Q0 measures a 1, then we apply a -1 operation. So if Q0 measures a 1, then we apply the phase flip gate, which was Z, and that's why we did it for both of these examples. And B2 is Q1 measured. If B2 is a 1, then we apply the bit flip gate, which is why they have a C naught right here, because the C naught is a bit flip gate depending on the measurement of the control qubit, or depending on the value of the control qubit, not necessarily the measurement. So that's in these two examples where Q1 is 1 and Q1 is 1, then we apply the X gate if needed. Okay. or sorry, in this example, not in this example. Here we don't apply anything. We just apply the identity. So that should cover all of quantum teleportation. So as a recap, what happens is we are using 3 total qubits to move the qubit state Q0 into Q2. And we do not have Q2's, Q2 does not reconstruct Q0 until Q0 is destroyed. So Q0 and Q2 can never have the same information at the same time. And then one more important thing is that Q1 and Q2 must be a shared bell pair between Alice and Bob prior to them leaving and splitting up and using quantum teleportation to do this. Okay, so that's the teleportation algorithm. I am now going to open up the superdense coding algorithm. Okay, so superdense coding instead is now between Alice and Bob. What amount of classical information can Alice send to Bob per qubit? So the reality is that using just 1 qubit communicated, you can, and I think actually you don't even need to, do you need to send the qubit? Yes, you do. So you have 2 bits of information, B0, B1 you start with, and you encode it into a qubit, Q0, and you send that Q0 qubit over a quantum channel to Bob. So for every single qubit you send to Bob, you encode 2 bits of information, B0 and B1. But the name is kind of misleading because Q0 and Q1, another qubit, must be entangled prior to this in a bell pair. And if you need 2 qubits or you need 1 pair for every 2 bits of information, then you're really sending it at the same rate of information or the same resource rate, but you encode it more densely in that if Alice and Bob split up, you only need to send 1 qubit across a physical channel to actually get the information reconstructed from B0, B1. So for this example, for this algorithm or circuit, superdense coding requires 2 total qubits, whereas quantum teleportation requires 3 total qubits. Okay, so let us look at the circuit with a walkthrough at each stage once again. So here, beta 0 and beta 1, they are 2 bits of information we want to transfer. And depending on their value, we're going to get different results. So let's say beta 0 and beta 1 are both 0. Let's say we want to transmit the information 0, 0 first for beta 0 and beta 1. I'll draw it as a table later, I think. Then at this stage right here, after applying the first phase flip, I believe, what happens is if A is, or if, sorry, I'm reading a different picture. A is my B0 here. If B0 is a 1, then you apply the Z gate to Q0. And let me confirm that's correct. Yeah. If it's a 1, you apply the Z gate. So if you apply the Z gate in this instance, or sorry, it's not a 1 in this instance, so you don't apply the Z gate. For this example, 0, 0, next, after that point, we check, is B1 a 1? If it is, then you apply a C0 onto Q0, which would be the X gate. And we don't have a 1 there, so we don't apply anything. So we just have 0, 0 here. And now the qubit state, Q0, Q1, is still the bell pair from earlier, right? Because nothing has changed with these 2 operations. So Q0, Q1 is equal to the bell pair, which is 1 over square root of 2 ket 0, 0 plus ket 1, 1. And that's from before doing any operations, and even after applying both of these operations, we still have the same bell pair state. Okay, now once we get to this stage in the circuit where we apply the C0 onto the qubit with Q0 as the control, what that does is we have 1 over square root of 2 times, we look at the first qubit, which is Q0, and we don't flip it because that's a 0. The second one we do flip. So now we have 0, 0 plus 1, 0. And then after applying Hadamard, we have, before applying Hadamard, we can actually break this down. So this is equal to 1 over square root of 2 times, and we can pull out the second qubit as a 0 because it's deterministic. So we have a 0 plus a 1, and this tensor product with ket 0. And this is the Hadamard state. Or it's not the Hadamard state, it's the plus state, which is the Hadamard applied to Q0, or applied to 0 if Q0 is equal to 0. So this is equal to ket plus 0, and this is the state of the two qubits after B0 and B1 are both 0. If this is the case, then we apply Hadamard at this final step right here, and H applied to the plus is going to become a 0. And the second qubit is untouched because there's no H gate applied to that one. So now we have uncovered 0, 0, and once we measure, we're going to get 0, 0 100% of the time because there is no superposition of 0 and some other basis vector, let's say 1, 0. So now, given the two bits being 0, 0, we can uncover the two qubits as 0, 0 once we measure them at the end. And that was sent using just one qubit, Q0. Now let's look at the next example where B0 and B1 are different. So remember we start Q0 and Q1 as 1 over square root of 2 times ket 0, 0 plus ket 1, 1, the perfect Bell pair. Let's say B0, B1 are 0 and 1. Now, once you go through the circuit at this stage, we're going to check, is B0 a 1? If so, then apply Z gate, which is not, so we don't do anything. And then at this stage, we check B1. If that's 1, apply C naught, which it is. So we apply the X gate. And here we have 1 over square root of 2 times ket 0. And we apply the X gate to the second qubit. We apply it to the first qubit because this is the target. So we have 1, 0, 1, 0 plus 0, 1. And this is the perfectly anticorrelated Bell state. So this is the state after applying everything up until this point. And if it wasn't clear because I'm like figuring this out as I go, the 1 is flipped from earlier because this is applied to Q0 as a target using whatever the value B1 is. Okay, so now we will go to this step right here. After applying the C naught between Q0 and Q1 and with Q0 as the control, we get 1 over square root of 2 times ket, and since this is a 1, the next one will become a 1. And since this is not a 1, the next one stays the same. And now we apply Hadamard, but before we apply Hadamard, let's factor this out. So we have 1 over square root of 2 times ket 1 plus ket 0, tensor product ket 1. This is equal to the plus state, so we have plus and then a 1. So after we apply Hadamard to that, we get 0, 1. And now we have recovered B0 and B1 as the 0 and 1 from earlier. We just have to now measure B0 and B1 here, or measure the two qubits Q0 and Q1, and we're going to get our result. Now let's look at the next example. So if we have a 1 and a 0 as our B0, B1, then what happens is it checks, is B0 1, then apply the Z gate. Since B0 is a 1, it applies the Z gate to Q0. So we have 1 over square root of 2. And remember, from the Bell pair, I'm going to apply the Z gate to this first example. That doesn't affect this because 0 doesn't have a phase. And then it's going to have a minus phase for the next one. So minus 1, 1, I believe. Yes. And this next one, if B1 is a 1, we just ignore it because B1 is 0 in this instance. Now we move on to this portion of the circuit we apply a C naught between Q0 and Q1, and we get 1 over square root of 2 times ket 0, 0 minus, and we apply the C naught to this, so we get 1, 0. And now let's factor it out again. So we'll pull out the 0 in the second portion. So we have 1 over square root of 2 times ket 0 minus ket 1, and then tensor product ket 0. And I'm not able to do it neatly, sorry. This right here is the minus state, and the next part is the 0 state. And then once we apply Hadamard to the minus state, we get 1, 0, which is, once we measure the 2 qubits, with full certainty, we're going to get the 1, 0 from earlier as well. Finally, let's look at the last example, especially because that one has a tricky part to it. B0, B1 are 1, 1. We apply to the bell pair, we check B0, we apply the Z gate first. So to the bell pair, we get 1 over square root of 2. The Z gate gets applied to Q0. So we get 0, 0 because there's no phase flip for 0. And then we get minus 1, 1. And then applying this next C naught onto Q0 as a target, we get 1 over square root of 2 times 0. With B1 affecting Q0, then I have to flip this actually. So this should be a 1, 0. And then it should be a minus 0, 1. So this is a perfectly anti-correlated Bell state with a phase flip. Now applying this portion right here, applying the C naught between Q0 and Q1, we get 1 over square root of 2, and applying Q0 as the control, then this flips, so we get 1, 1, minus, and this one does not flip, 0, 1. And then applying, or we don't have to apply Hadamard yet. First, we factor it out. 1 over square root of 2 times ket 1 minus ket 0, tensor product ket 1. This state right here is equal to the negative, it's equal to the negative minus state. So this is not just equal to the minus state, because the minus state is ket 0 minus ket 1. So it's equal to negative minus state. And once we apply Hadamard to this, we get negative, and this is a 1, 1. And once we measure this in the end, I think I messed up in teleportation and said there was supposed to be a negative where the measurement didn't care about the negative. That applies here instead. So once you measure these 2 qubits, the negative won't affect the measurement, and we're still going to get our 1, 1 as promised earlier. So using just 1 qubit sent over a quantum channel, which is this portion right here, this line right here, we are able to transmit 2 bits of information. But of course, we still need 2 qubits per bit. It's just physically we don't need to send 2 qubits. Okay, that is all the algorithms. That should be all of entanglement. I apologize if I got mixed up in certain places, but you got it now. Good job.